The world we inhabit is dazzling, turbulent, and overwhelmingly complex. Waves crash, clouds assemble and dissolve, forests bend in invisible currents of air. Everywhere we look, motion collides with motion, color blends into color, and noise folds into deeper noise. It appears chaotic, almost reckless in its variety. Yet beneath this riot of sensation, we carry a persistent intuition that something steadier is at work. We suspect that hidden under the disorder lies a structure, a pattern, a logic quietly guiding events. We feel that reality is not random turbulence, but an intricate performance governed by rules. Imagine that existence is like a vast chess match played by unseen hands. The board stretches infinitely in every direction, so we never glimpse its edges. The pieces are too small to inspect clearly, and the players never explain their strategies. We sit in the audience, watching silent moves unfold. A piece shifts, another vanishes, and we attempt to infer the rules. We guess patterns from repetition. We build expectations from observation. This guessing game, this careful decoding of motion, is what we call physics. It is our attempt to reverse engineer the rules of the cosmic game. Yet something unsettling lurks beneath this process. The rules we write in our notebooks, the formulas we carefully derive, are expressed in mathematics. Mathematics is something we invented, at least it seems so. We defined numbers, created symbols, imagined triangles, and constructed calculus to describe change. These ideas arose in human minds. They were shaped by thought, not discovered lying in a forest or buried in stone. So why should the universe, vast and indifferent, obey equations we dreamed up? Why should reality conform to abstractions born from imagination? This is the great mystery, the unreasonable effectiveness of mathematics. We could imagine a universe with no stable patterns, where laws shift unpredictably or dissolve entirely. A world where gravity weakens every Tuesday, or where objects fall upward without explanation. But our universe behaves differently. Its patterns persist. If we write the correct equations, we can predict eclipses centuries ahead. We can design bridges that stand firm and spacecraft that navigate distant worlds. It almost seems as if the universe speaks mathematics fluently, as though equations are etched into its foundation. But that explanation troubles us too. If mathematics is merely a human invention, how can it so perfectly describe the cosmos? Did we invent the language, or did we discover it? Perhaps mathematics is not created but uncovered, like a continent emerging from fog. There appears to be a deep resonance between the logic of the human mind and the logic of nature. Our thoughts, shaped by evolution on a small planet, somehow mirror the architecture of galaxies. This connection remains mysterious, bridging consciousness and cosmos in ways we barely comprehend. Long before modern science, ancient civilizations searched for order in the sky. The Babylonians tracked lunar cycles with meticulous records. They predicted celestial events using tables of numbers. Their system worked even if they lacked geometric explanations. Similarly, the Maya charted eclipses with astonishing precision. They recognized patterns without fully understanding the mechanisms behind them. They were observers of repetition, guardians of numerical rhythms. Though they did not conceive of Earth orbiting the sun, they demonstrated that nature could be anticipated through systematic record and careful counting. Centuries later, Isaac Newton unified heaven and earth with mathematics. He wondered whether the force pulling an apple downward might also guide the moon's orbit. This was not obvious. Apples fall straight, moons circle gracefully. Yet Newton proposed that both motions arose from the same principle, gravity. He developed calculus to describe continuous change and applied geometric insight to motion. From this synthesis came a simple formula describing gravitational attraction. Suddenly, falling fruit and orbiting planets shared a single explanation, bound together by algebraic clarity. Albert Einstein revolutionized this picture. He questioned action at a distance. How could Earth instantly feel the sun's pull? If the sun vanished, would Earth respond immediately? Newton's framework implied yes. Einstein disagreed, insisting that nothing travels faster than light. To resolve this tension, he reimagined gravity not as a force, but as geometry. Space and time became a flexible fabric, curved by mass and energy. Objects followed the contours of this curvature, tracing paths determined by warped spacetime itself. When we descend to the quantum realm, our intuition falters entirely. Particles behave neither like classical objects nor simple waves. Instead, they follow rules encoded in probabilities and complex amplitudes. The familiar dissolves into strangeness. Physicists admit that while calculations succeed brilliantly, conceptual understanding lags behind. Quantum mechanics challenges our deepest assumptions about determinism, locality, and reality itself. The melody of nature plays continuously, whether or not we listen. Mathematics allows us to hear fragments of that music. Though we invented notation, the harmony precedes us. If someday every mystery were solved, curiosity would fade and the game would end. Fortunately, reality remains deeper than comprehension. Its strangeness ensures endless discovery. The world is more mathematical and more mysterious than we ever imagined, and that enduring mystery keeps the adventure alive.